So our second speaker of the day is Tom Rudelius from Berkeley, who's going to tell us about higher group symmetries, Axion strings, and weak gravity conjecture mixing. Tom, I will give you a 20-minute notice that you have 5 more minutes. Please go ahead.
Okay, great. So yeah, thank you to the organizers for the invitation to speak here. Thank you also for letting me go in the second slot. It's nice being on the West Coast, having to get up pretty early to have another half hour to get ready. So indeed, I'll be talking today about higher group symmetries, Axion strings, weak gravity conjecture mixing, and this talk is going to be based primarily on some work that I did with Sami Kaya, who's a graduate student at Berkeley, as well as Ben Heidenreich and Matt Reese, but also touch a little bit on some more recent work of mine with Clay Cordova and Kantaro Omori. So first of all, let me start off by telling you what are the main takeaways from my talk, and then I'll elaborate on each of these and remind you of them again at the end. So first of all, I'm going to review the notion of a higher form symmetry. These are symmetries whose charged operators are higher dimensional. I'm then going to review the notion of a higher group symmetry. This is a symmetry structure in which two or more higher form symmetries are mixed up with one another in a certain way. We're then going to see that this mixing up of higher form symmetries mixing up of emergent higher form symmetries can lead to an analogous mixing up of weak gravity conjectures. And this is mirrored in supergravity. And the main takeaway here, the main point of all of this, is that much of the swampland program can be understood in terms of generalized global symmetries and their gauging and breaking. So first of all, then let's talk about higher form global symmetries. These were introduced to the quantum field theory community by Gaeta, Kabustin, Seiberg, and Willett in 2014. And the idea here is that we have a Q-form global symmetry when we have some symmetry for which the charged operators live on Q-dimensional manifolds. So for instance, an ordinary symmetry has charged operators which are just local operators associated with zero-dimensional manifolds, points in space-time. So this corresponds to the case of a zero-form global symmetry. In a higher form symmetry, then, with Q greater than 0, the operators will be extended. They won't be local operators, but rather they'll be line operators or surface operators or something like this. Global symmetry transformations form a group, G, which can be either discrete or continuous. In the case of an ordinary global symmetry, it can be non-abelian or abelian. But for a higher form symmetry, it's necessarily abelian. If G is continuous, then under reasonable circumstances, there will be a conserved D minus Q minus 1 form, another current, J. A D minus Q minus 1 form is something that can be integrated over a manifold of dimension D minus Q minus 1. And the statement that is conserved means that this differential form, J, is closed. So dj equals 0. A prototypical example of this is U1 gauge theory. So if we suppose we just have pure U1 gauge theory, no charged matter, no monopoles, then we're actually going to have not just one, but two higher form symmetries. In 4 dimensions, both of these are one-form symmetries. There's an electric one and a magnetic one. The associated other currents are 2 forms. They're given up to normalization by star F and F, respectively. And their conservation follows simply from Maxwell's equations. In the absence of electrically charged particles or magnetic monopoles, D star F equals 0 and DF equals 0. These are both one-form symmetries. Their charged operators are one-dimensional. And in particular, they're going to be the Wilson lines and the 't Hooft lines, respectively. Now, this symmetry can be broken in the presence of charged matter. So, for instance, focusing now on the electric symmetry, if we suppose that we add in some charged particle, say a fermion, into our theory, then the equation of motion will be modified. Maxwell's equations will be modified. Instead of d star f equals 0, we'll instead have d star f equals some fermion bilinear. In other words, the one-form symmetry is broken by this fermion. In fact, it will be broken to a Zn subgroup for a charge n particle. So if this is charge 1, then it will be broken completely. It's interesting, though, to consider a couple of different limits of this theory. So first of all, in the g goes to 0 limit, you'll see that this term on the right-hand side goes to 0. And indeed, the one-form symmetry is restored as in this g goes to 0 limit. On the other hand, you can consider that m goes to infinity limit. In this case, you can integrate out the fermion at low energies. And at low energies, you'll again just have d star f equals 0. So in either the g goes to 0 limit or the m goes to infinity limit, we see that this one-form symmetry will be restored. And the reason this is interesting is that these are precisely the limits that are forbidden by the weak gravity conjecture. In an abelian gauge theory, the weak gravity conjecture places a lower bound on the charge to mass ratio of a charged particle. It says that the charge to mass ratio has to be order 1 in Planck units or larger. Here, if g goes to 0 with fixed m, or m goes to infinity at fixed g, then the charge to mass ratio will go to 0 and violate the weak gravity conjecture. So we see here that the absence of this one-form symmetry is closely related to satisfying the weak gravity conjecture. This is a very hand-wavy argument, but in my paper with Clay Cordova and Kantaro Omori, we gave a more quantitative argument for explaining the relationship between the absence of this one-form symmetry and the weak gravity conjecture. So I could go into that further, but instead, for today, I'm going to switch gears a little bit and now talk a little bit about higher group symmetries. So suppose that we have some collection of n higher form symmetries, which are pk form symmetries. So they don't all have to have the same, they don't have to all be the same form degree. Now, what we can do is we can couple each of these pk form symmetries to background gauge fields. And this background gauge field is going to be a pk plus 1 form. So for instance, in the case of an ordinary symmetry, where pk is equal to 0, this is just a one-form gauge field, like we're familiar with from electromagnetism. Now, a background gauge field will ordinarily have a transformation law, which goes like this. A goes to A plus d lambda. That's the classic gauge transformation that we're familiar with from electromagnetism. But what can happen in this theory with a collection of higher form symmetries is that we can have additional terms like this, where the gauge transformation of AK depends on the gauge parameters for the other background gauge fields. There could also be some Schwinger terms involving 2 or more powers, 2 or more factors of these gauge parameters. But it's this term here, really, which is the hallmark of a higher group symmetry. In a higher group symmetry, the background gauge fields for some p-form symmetry transform under the background gauge transformations for some other global symmetry, according to this term here. So a prototypical example of this, which will play an important role shortly in our discussion of the weak gravity conjecture, involves theories where we have 2 gauge fields coupling via a Chern-Simons term. So here we have a gauge field A with field strength F. We have a gauge field C with field strength G. So these are just the ordinary kinetic terms. And then we have this Chern-Simons coupling, which couples one gauge field to the other. Now, we saw earlier that in electromagnetism, there are 2 background, two higher form global symmetries, an electric one and a magnetic one. This is still going to be true in this theory, but now there's also going to be an electric symmetry and a magnetic symmetry for this gauge field. So in total, there are 2 electric symmetries under which the Wilson lines of F and G are charged, respectively. And then there's 2 magnetic symmetries under which the 't Hooft operators of F and G are charged. So we can therefore couple this system to background gauge fields for these respective higher higher form symmetries. So we can couple F and G to the background electric gauge fields for the electric global symmetries, like so. And then we can also couple the gauge fields A and C to the background magnetic gauge fields. And then we also have this additional coupling, the Chern-Simons coupling, where the electric background gauge fields make an appearance. Now, in this theory, we're going to have background gauge transformations. For the electric one, or the electric ones, the transformations are ordinary. We just have A goes to A plus D lambda, C goes to C plus D lambda. And here you'll note the superscript E shows that we're referring to the electric guys. On the other hand, the magnetic background gauge transformations will be modified. We have A goes to A plus D lambda, but then we also have these additional terms. Same thing for the magnetic background gauge field for C. And you'll note these terms here are the ones that are the hallmark of the higher group symmetry. So in the presence of this Chern-Simons coupling, the magnetic and electric background gauge fields here are mixed up into a higher group structure. And you'll note that indeed, if K is equal to 0, so if you take K to 0 and you get rid of this Chern-Simons coupling, then all of these terms go away, and you just have ordinary transformation laws. Now, in the presence of these modified background gauge transformations, we'll also have modified field strengths, because DAM and DCM are no longer gauge invariants due to these additional transformations. So to make a gauge invariant field strength, we need to add in these additional terms. And I especially want to draw your attention here to the second equation, because what you'll note from this equation is that if you turn on a background for A2E, the electric, a background for the electric global symmetry for the gauge field A, this equation is telling you that turning on a background for AE automatically turns on a background for CM, because if this is non-zero, then G4M will also be non-zero. And if you imagine a scenario in which this higher group symmetry is emergent, it shows up at low energies below some energy scale. What this equation is telling you is that the emergent scale for this electric one-form symmetry must be below the emergent scale for the magnetic two-form symmetry here. Because whenever this is a valid symmetry, this must also be a valid symmetry, because this electric background gauge field turns on this magnetic background gauge field. So as noted by Brennan and Cordova, we have, from the consistency of the higher group symmetry, we have this relationship on the emergent scales for this symmetry and this symmetry. Now, what does this have to do with the weak gravity conjecture? Well, first of all, let me remind you that the weak gravity conjecture is not just a conjecture about particles charged under ordinary gauge fields, but also more generally for branes charged under p-form gauge fields. When you have some particle charged under a one form, we saw the weak gravity conjecture places a lower bound on the charge to mass ratio. But more generally, the weak gravity conjecture gives a lower bound on the charge to tension ratio of charged objects under p-form gauge fields. So we saw a slide ago that the consistency of the higher group symmetry gives us this bound on the emergent scales for the electric one-form symmetry, the magnetic two-form symmetry for C. We saw also in the first part of this talk that the electric one-form symmetry of A is broken by charged particles. And if we're below the masses of all of these charged particles, then we can integrate them out and the symmetry will be restored. We'll have an emergent one-form symmetry. So this means that the mass of the lightest charged particle is necessarily below the emergent scale for this one-form symmetry. On the other hand, as argued by Brennan and Cordova in the same paper, the two-form magnetic symmetry of C is going to be broken at or below the charged string scale. So if we have some string which is charged magnetically under C, then the energy scale at which the two-form symmetry emerges is going to be below the square root of the tension of the string. And so if you combine these three inequalities, we learn that the mass of the lightest charged particle has to be smaller than the square root of the tension of the charged string for consistency of the higher group structure. Now, here's where the weak gravity conjecture comes in. Suppose that in this theory, we assume that the weak gravity conjecture is satisfied for the gauge field C. This implies that there will be some instanton, some codimension 4 object, whose tension is smaller than GC in Planck units. We're also going to assume the magnetic weak gravity conjecture for C, which tells us that there should be some charged string, charged magnetically under C, whose tension satisfies this inequality. We further make an assumption about this instanton tension. Namely, we assume that it goes like 1 over GA squared. This relationship is familiar from QCD. The QCD instanton action is equal to 8 pi squared over G squared. And that's 1 over G squared is the same thing we're seeing here. In the presence of the Chern-Simons coupling, we expect this sort of behavior, as argued by John Stout, Matt Reese, and collaborators from computations of monopole loops. So the upshot of all of these inequalities, if we stick these relations together, we find that the string scale, the square root of the tension of the string, should be smaller than GA in Planck units. And if we combine this with our bound on the previous slide, that the mass of the lightest charged particle should be smaller than the square root of the tension of this string, what this tells us is that the mass of the lightest charged particle should be smaller than GA in Planck units. And this right here is, up to order 1 factors, nothing but the weak gravity conjecture for the gauge field A. Mass is smaller than charge. Okay, so let's take stock for a moment. What have we done here? Why is this an important result? Well, in this theory with the Chern-Simons coupling, we have assumed that the weak gravity conjecture and the magnetic weak gravity conjecture is satisfied for the gauge field C. We've made no assumptions about the weak gravity conjecture for the gauge field A. But we have assumed consistency of the higher group emergent symmetry. And what we see here is that consistency of the higher group symmetry, as well as the weak gravity conjectures for C, immediately gives us the weak gravity conjecture for A. So this is what I refer to as weak gravity conjecture mixing. Just as how the higher form symmetries are mixed up into a higher group structure, so too are these weak gravity conjectures mixed up, such that the weak gravity conjectures for C immediately imply the weak gravity conjecture for A. Now this in turn will have some interesting phenomenological consequences. So let's focus now our attention on the case of 4 dimensions. Here we have the gauge field C becomes an axion. The axion weak gravity conjecture gives us this bound. The weak gravity conjecture for the axion strings gives us this bound. We have our assumption that the instanton action goes like 1 over G squared. And when we put these together, we find that the string scale should be smaller than G m Planck. So at this point, we can argue, once again, on the basis of the consistency of the higher form structure, higher group structure, that the mass of the lightest charged particle has to be less than G m Planck. Alternatively, we can also argue that due to anomaly inflow from the theta F-Jeff term, that the string excitations must carry electric charge. These string excitations will have a mass that's of order the string scale. And if they carry charge, that means that the lightest charged particle, the string excitations, will satisfy the weak gravity conjecture. So not only do we see here that these charge states must satisfy the weak gravity conjecture for consistency of the higher group emergence bound, we also learn a little bit more about the nature of these weak gravity conjecture satisfying states. Namely, they're stringy in nature. They're the string excitations of the axion string. And if this axion is a fundamental axion, meaning that the core of its axion string probes the deep ultraviolet, then we'll actually have not just a single superextremal string excitation, but a whole infinite tower of them, satisfying not only the ordinary weak gravity conjecture, but also the tower weak gravity conjecture, which requires this whole infinite tower of superextremal weak gravity conjecture satisfying states. This is important for phenomenology for the following reason. It's been argued, it was argued a number of years ago by Ben Heidenreich, Matt Rees, and myself, that in theories that satisfy the Tower or sublattice weak gravity conjecture, there will be a breakdown of effective field theory at the so-called species. In the presence of the theta Fydjeff term, however, we're actually seeing here that effective field theory breaks down at a lower energy scale, the string scale, which goes like EM Planck, due to the anomaly inflow, or alternatively, consistency of the higher group symmetry. When E is small, this energy scale will be far below this one. So in other words, in the presence of this theta Fydjeff term, we're seeing that effective field theory is breaking down prematurely. This is important for model building because if you have some theory that requires a very high energy scale, like for instance, a grand unified theory, large field inflation, etc. What we find here is that there will be an incompatibility between this theory and a theory that has a very tiny coupling constant E, such as chromonatural inflation or dark radiation. So it's important from a model building perspective to know whether effective field theory will break down at the energy scale EM Planck or E to the 1/3 M Planck, especially if you want to build some high energy theory like a grand unified theory or large field inflation. And what we're seeing here is that actually these high energy effects are encoded in just the low energy presence or absence of the Chern-Simons term theta Fydjeff. In the absence, we'll have these looser constraints on high energy effective field theory. In the presence of this term, we'll have tighter constraints.
Now, Tom, you have 5 minutes.
Perfect, thank you. Now, the argument I gave originally for this, for the weak gravity conjecture here, you'll note, wasn't specific to 4 dimensions. Of course, if we're interested in phenomenology, then 4D is the most important case. But it's interesting to ask, do we see this this structure and this weak gravity conjecture mixing showing up in higher dimensions as well? So in 5 dimensions, it turns out that this sort of consistency with the higher group symmetry and weak gravity conjecture mixing is actually encoded in the supergravity, the structure of supergravity itself. So suppose that we have a supergravity theory in 5 dimensions with 2 abelian gauge fields, A and B. Using the cubic structure of the prepotential in 5 dimensions, one can show that there are 2 cases. One is if we have a Chern-Simons coupling of the form B Fydjeff, then there will be a scaling relation between the gauge coupling for B and the gauge coupling for A, which goes like this: GB scales as GA to the -2. So in a limit as GA goes to 0, if we assume that the weak gravity conjecture is satisfied for the magnetic strings charged magnetically under B, then we'll see that the square root of the tension of these strings goes like GA. And this, you remember, is exactly what we needed for the weak gravity conjecture. Consistency of the higher group symmetry therefore implies that the lightest charged particle charged under B will have a mass smaller than this, charged under A, will have a mass which is smaller than this, and therefore it will satisfy the weak gravity conjecture for A. On the other hand, if there's no such coupling of this form, then there will be a different scaling relationship between the gauge coupling for B and the gauge coupling for A. And instead of the square root of the tensions going like GA, it will instead go like GA to the 1/4, which incidentally, if A is a Kaluza-Klein gauge field, this is going to be simply the Planck scale in 6 dimensions. So we have 2 cases here. If there is this coupling, then the weak gravity conjecture tower will be a stringy one. If there is no such coupling, then it won't. And in fact, in the case where this is a Kaluza-Klein photon, this will be a Kaluza-Klein, a tower of Kaluza-Klein modes. So these 2 cases correspond to the so-called emergent string limit and the decompactification limit, which Lee, Lerche, and Huygens argued were the only 2 possibilities for what can happen in infinite distance in 5 dimensions. So what we're seeing here is that the 2 cases of Lee, Lerche, and Huygens are actually encoded in the presence or the absence of these cubic terms in the action, these Chern-Simons couplings. Analogous results, it turns out, hold in 6, 7, 8, 9, and 10 dimensions as well. Whenever you have a Chern-Simons coupling of this form, you'll always have this scaling relation, which implies that there's this weak gravity conjecture mixing as required for consistency of the higher group symmetry. And when there is no such coupling, there will not be this scaling relation, there will be a different one. In other words here, what's happening is that supergravity in higher dimensions is smart enough to know what it needs, what sort of scaling relation it needs to have for consistency with weak gravity conjecture. So in conclusion, let me remind you the main takeaways. First of all, higher form symmetries are symmetries involving charged operators of higher dimension. 2 or more of these can be mixed up into a higher group symmetry. And in theories with emergent higher group symmetries, there's an analogous mixing up of weak gravity conjectures, which is encoded in supergravity and can lead to important phenomenological implications in 4 dimensions. Really the main point here, which is the point that underlies a lot of my recent work on the swampland, is that much of this whole swampland program can be understood in terms of the breaking of generalized global symmetries. The absence of global symmetries in quantum gravity implies many other important statements about the swampland as well. So some interesting open questions that I'll conclude with here. First of all, when exactly are theta FOJF couplings? We've seen so far that the presence or absence of these terms has important phenomenological consequences. We've also seen that the only example really that we're familiar with where these terms are absent is Kaluza-Klein theory. Is this really the only case, or are there other examples that don't have these sorts of couplings? Is there an analog of the convex hull condition for these higher group global symmetries? And finally, I've focused today on one particular example of a higher group symmetry where we have this C wedge F Chern-Simons coupling. But there are more general Chern-Simons couplings as well, which lead to more general higher group symmetries. And it would be interesting to study weak gravity conjecture mixing in these contexts as well. Thank you.
Thank you very much. We have time for some questions. Raise your hand or unmute yourself if you have any. I have some if you want me to warm up. Maybe let me start. Oh, or Jim, go ahead.
You can go. You were about to ask a question. I'll go after you, Pablo.
Well, okay, let me ask my question. So when you were in the example you gave in which you were mixing the weak gravity conjecture for axions and standard gauge fields, there was these extra assumptions that the instanton action behaved like 1/g², which is quite reasonable, but it doesn't really derive directly from weak gravity conjecture from swampland considerations. But when you go to higher dimensions and you mix higher order symmetries, what is the analog statement, or do you need something like that?
Yeah, good. Yes, so you you still in fact need this relationship here, where so here in 4 dimensions, right, the instanton is a -1 brane. In higher dimensions, it will be a p brane where p is greater than -1. And the tension of this brane must satisfy this expression here. So the way to argue for this that I'm familiar with is there's this paper, as I mentioned, by John Stout, Matt Reese, and some of their collaborators, whose names are escaping me at the moment. I apologize to the other collaborators on that paper. But what they argued is that when you in 4 dimensions, when you have monopole loops will generate potential for the axion.
Oh, sorry. generated potential for the axion with instanton action that goes like this. And that argument should work in higher dimensions as well if you kind of just let the other dimensions come along for the ride. So the argument is that in the presence of the Chern-Simons coupling, that you should have this relationship. Now, in the case of supergravity, what we're seeing here is that actually supergravity has this built into it in higher dimensions. But my claim is that this relationship shouldn't necessarily rely on supersymmetry. So I think if you drop the constraints of supersymmetry, you'll still see this. But when you impose supersymmetry, this follows immediately. So I guess it would
not just for
it would
instantons.
be interesting to study it further in the non-supersymmetric context. Yeah.
Thank you. Jim?
Hi, Tom. Great talk. Can you go to your last slide real quick? The conclusion slide. So, no, sorry, the one after this. Yeah, so I was wondering if you might comment a little bit on connections between what you're saying and the generalized Green-Schwarz mechanism. So these theta F wedge F terms are absolutely crucial in that case to cancel anomalies. And I was wondering if you could just comment on how to understand the interplay between these things.
Yeah. So I know that the higher group symmetries should be sort of understand as like a Green-Schwarz mechanism for background gauge fields. And so in this case, you have sort of this mixing up of the gauge fields as occurs in the Green-Schwarz mechanism, and then this in turn leads to a mixing up of their background gauge fields. I think one thing, yeah, that's worth emphasizing further is that indeed, as you talk about the canceling of anomalies, we're going to have some anomaly inflow on the in the string world sheet here in coming in theories with these terms, which has to be canceled. And in canceling this, you essentially learn that the string excitations have to carry electric charge. So this fact, which ensures the weak gravity conjecture, is also related to the canceling of the anomalies through this Green-Schwarz term. So yeah, certainly these ideas are all very closely related.
Okay, so you're saying that there's sort of a higher dimensional origin of this, of ways to think about the mixing being related to Green-Schwarz in general, and this is like a lower dimensional avatar.
I think that's right. Yeah.
Good. I do have one more question. In this case where you're talking about the UV cutoff scaling differently with E in this context.
Yeah.
So there's so the work out of the Cornell group and others the last few years teaches us that, generally divisors are going to be large and couplings are going to be weak. What exactly, again, should I really be? I mean, so the UV scale indeed is lower than one would have expected given the bottom scaling relation as opposed to the top. What concretely should one be looking for in terms of the effective theory for where it breaks down? This is just my lack of knowledge.
Yeah. Okay. Good. Yeah. So good. So I can't say that there might be something, some other phenomenon which comes in at a lower energy scale and breaks the effective field theory further. Say a very large volume or something like this, and the higher dimensional Planck scale is lower. But here's where these breakdowns are coming from. So in this first case, we're assuming that the tower weak gravity conjecture is satisfied, which means we have a tower of charged particles, and these things will run in loops and correct the graviton propagator. And as a result, gravity will become strongly coupled at this lower so-called species bound scale. And in the case where these conjectures are satisfied, one can relate the square root of the number of species, which shows up in the species bound, to the gauge coupling in this manner. And so as E goes very small, there will be more and more light states, and they'll lead to this breakdown. In this case, effective field theory is breaking down for a different reason. It's not breaking down because gravity is becoming strongly coupled. It's breaking down because this is the string scale. We have this string, this axion string, which is charged magnetically under theta. And what we've seen here is that the string scale will go like the gauge coupling times m Planck. And so in this case, what's happening is gravity is becoming strongly coupled. In this case, what's happening is that there's this light string. There may be other reasons why effective field theory might break down even at an even lower scale, but this is sort of the upper bound. So I guess I should have a less than here. Yeah.
I see, that makes sense. So in the context of those geometric setups, good. So divisors are becoming large, and that's correlating with small gauge couplings. And okay, good. And so
Exactly,
you should be looking for the fundamental scale of the string going to 0. Okay.
Exactly. Yeah. Exactly. That's right.
Okay. Thanks.
May I ask something?
Please go ahead.
Yes. So what if your theta that is crucial for this term theta ff? If your theta is originally there, but it's removed because it is gauged by some other U1, such often happens in string theory. Which
so like a Stuckelberg mechanism?
Yes. Which class of theories am I in then? As an IR effective field theorist, I don't know that originally there was some theta which has been removed. So it's not so clear which setting I'm in.
Yeah, that's a good question. Okay, so I hadn't thought about this, but what I can say is, when theta is eaten, when it's made massive by the Stuckelberg mechanism, then at low energies, I believe you're not going to have the emergent higher group symmetry, because essentially it's gauged away. I think that's right. So I think it's what you might suppose is that there's sort of like an intermediate energy scale, at which you have this higher group symmetry, and at low energies it's broken because theta is eaten, and at high energies it's broken because well, essentially you break these symmetries by charged particles and strings. In fact, I guess I did talk a little bit about BF couplings and weak gravity conjecture mixing in that case in my paper with Sami Kaya. So if you, I guess I'll point you to that paper. I didn't look at it in this theory. I looked at it just, I didn't look at it in the presence of this coupling. I just said, let's suppose that there's a BF coupling. And what you see there is that there's sort of a weak gravity conjecture mixing that goes on, but the relationship with higher group symmetries is much weaker. And relatedly, the bounds aren't as sharp as they are as the ones that I discussed here today. So yeah, I'll point you to that, to the last section of our paper.
Tom, just one more quick comment, since you mentioned this BF, you mentioned B wedge F and also this theta F wedge F term. So something that was existing in the literature a couple of years before I started grad school were these cases in type 2 compactifications where you have a Stuckelberg U1, but it's actually non-anomalous. And so the way that should be understood is that you have the B wedge F, but not the theta F wedge F coupling. I don't know if that's something you've thought about or if it would be interesting to point you to the references, but it's sort of exactly this case where you do have the Stuckelberg, but you don't have the other term. And so you could study one case or the other in that context.
Oh, that's interesting. Yeah. Yes. Yeah, I think it would be really interesting to look at how the old results from that older literature. I suspect that there's probably a sort of a more modern way to understand these in the language of these higher group symmetries. So I think it would be really interesting to see what's going on there. Yeah. So yeah, feel free to send me those references.
Thanks for the great talk.
Yeah, thanks.
All right, thanks very much, everyone, for the interesting questions. We run out of time, so I think we can wrap up now. Let's thank both speakers today once more for the very nice talks. And let's meet again next week for another session of the seminars. Bye, everyone.